Hello, physical science students, and welcome to this video that deals with magnetism. We're going to talk about magnets, obviously, magnetic fields, magnetic poles, Earth's magnetic fields, different magnetic materials, magnetic domains, and permanent magnets. So, to give you a little bit of history, over 2,000 years ago, the Greeks actually discovered deposits of a mineral that was a natural magnet. This mineral was later named magnetite, and that's what we know it as today. It is a magnetic stone. Before that, the Chinese had actually invented the compass a couple hundred years prior to that, during the Han Dynasty, and about 1,000 years ago, the Chinese used that to navigate at sea. So it isn't known exactly the workings of this, but they've known about magnets for a very, very long time. Today in science, we use the word magnetism to refer to any properties or interactions of magnets. A magnet? What is a magnet anyway? Well, it's surrounded by a magnetic field, and that field exerts a force on other magnetic materials. And you've had hopefully an opportunity to play with magnets in your life. These are fun magnetic toys to play with. If you haven't actually had an opportunity to play with magnets, please try and do so in class. I have a few magnets that are fun to play with. Here's a picture of common magnets. Many of the devices that we use today have magnets in them. Fuel gauges and speakers and many electronic devices use magnets. Some interesting properties about magnets. They will sound very familiar to you since we've just studied electricity and gravity as well. Magnets either repel or attract each other, similar to electrical charge. And the force between magnets depends on two things: the strength of the magnet and the distance between them. It's very similar to other forces that we've looked at. You know that if you have played with magnets, you know that if they are farther apart, they will not have as great a force between them, whether it's an attractive force or a repelling force. There are also very different strengths of magnets. Here's kind of a weak magnet, picking up some paper clips. This is obviously a very strong magnet. And the strength of that magnet will definitely affect the force. So let's talk about the magnetic field. The magnetic field is simply the region of space surrounding a magnet. It exerts a force on other magnets and on objects made of magnetic materials. A stronger magnet will have a stronger magnetic field and will exert a stronger force on other magnetic objects and objects made of magnetic materials. A weaker magnet will have a weaker magnetic field and therefore exerts a weaker force. This is a pretty strong magnet right there. A magnetic field can be represented by magnetic field lines. These lines indicate force. And here are some examples. On this magnet here, we have these magnetic field lines traveling from the north to the south. And those are showing the lines of force. Here on this bar magnet, we have magnetic field lines traveling in this direction from north to south, as the convention goes. The magnetic field lines have a direction, and that's because force has a direction. It's a unit that has a very specific direction to it, and the force always points away from north poles, and it always points toward south poles. That's just the convention that we use. So in this case, where we have a disk magnet, these field lines are pointing away from the North Pole and toward the South Pole. Iron filings are a magnetic material, and if they are sprinkled around a magnet, they will line up along the magnetic field lines. And this is a picture of a bar magnet with iron filings sprinkled around it, and you can see that the iron filings line up along these field lines. So let's talk about magnetic poles. You've all heard of those. The magnetic poles are simply the regions of the magnet that exert the strongest force. It is where the magnetic field lines are closest together. And you can see that here. Here is a pole and here is a pole. All magnets have north and south poles. Poles that are alike repel each other, and opposite poles attract each other. This should sound very familiar to some of the principles that we've already discussed regarding electrical charges. Here we have a picture of different magnets that whose poles are being placed near each other. Here we have a bar magnet, just one of them, and here are its field lines. Then we have two bar magnets with poles placed near each other. Here we have attractive poles being placed near each other, and you can see that their magnetic fields combine and interact here. Here we have two north poles being placed near each other, and we can see how their magnetic fields combine. So when magnetic poles are placed near each other, their magnetic fields combine. Here is a picture showing another interesting phenomenon about magnetic field lines. If we place a compass anywhere around there, that compass needle will line up along the magnetic field lines as well. So let's talk a little bit about Earth's magnetic field, because that is actually where we get our definition for a magnet's north pole. The Earth's magnetic field, you may think of it as being very strong, but it is really not strong at all compared to common magnets. In fact, the magnetic field of a refrigerator is 100 times stronger than the Earth's magnetic field. The definition of a magnet's north pole comes from Earth's magnetic field. It is defined as the end that points toward Earth's geographic north pole. Now, here's something to keep in mind. Opposites attract. So, Earth's south magnetic pole is actually near Earth's geographic north pole. So the magnetic pole, the south magnetic pole for Earth, it actually aligns toward the geographic north pole. So keep in mind that the magnetic poles are different from what we term the geographic poles. And this shows that. If we look at Earth here, and this is our geographic north, and this is where we would think of the North Pole as being, that is in fact where the magnetic South Pole is. And here are the way the magnetic fields are placed around Earth. Another thing to keep in mind is that Earth's magnetic poles move very, very slowly over time. They have switched places in the past, about 150 times they've switched places in the last 70 million years, so they're not going anywhere really fast. The source of Earth's magnetic field is uncertain. It's hypothesized that it could be the circulating molten iron and nickel in the outer core. That is the hypothesis, and maybe you can go into physics and study more about magnetic fields and come up with the answer someday. So you all know not all metals are magnetic. Iron, cobalt, nickel are attracted by magnets, or they can be made into permanent magnets. And the reason for this is, you know that electrons are part of all elements. All atoms have electrons in them. And electrons have magnetic properties. And in almost all of the elements, these properties cancel out, but they just don't happen to cancel out in these elements. However, you also know that just because something is made from iron, it isn't always magnetic, right? So where do we get these magnetic properties? How do we get a magnet? How does that happen? I mean, an example would be a nail. You could have a nail that is magnetic, or you could have one that you you just drop it when it's next to a magnet. It isn't magnetic. Why is that, and what is the case? We're going to look at a model for this idea of unmagnetized and magnetized metals. So this idea of magnetic domains is a model for understanding magnetic properties, and it's easily seen here in this picture. When we think of unmagnetized groups of atoms, we can think of them as just being randomly organized. Their poles, their magnetic poles, are not aligned. When we talk about magnetic domains, we're talking about groups of atoms with aligned magnetic poles. In other words, they're organized in a way where all the norths are pointing in the same direction and all the souths are pointing in the same direction. Then if we get groups of domains in a material, in a larger chunk of material, if those domains are all aligned, then that larger magnet will have a north and a south pole. So how can we get the domains to be aligned like this? Well, we can place that material in a magnetic field. And that brings us to the idea of a permanent magnet. Any magnet whose domains remain aligned without an external field is called a permanent magnet, and it doesn't matter how long. It can be for a pretty short time. Certainly they don't have to be aligned forever. But if they're aligned for any length of time whatsoever, they're called a permanent magnet. It means they do not need that external field being there in order for their domains to remain aligned. And to make a permanent magnet, there are a couple of ways we can do that. We need to place that material in a magnetic field long enough so that those domains align and they remain aligned at least for a little while. One way we can do that is to stroke the magnetic material with a magnet. Here is, it sounds kind of strange, doesn't it? Here is an example of how to make a compass, some directions for that. If you want a little advanced proficiency, make your own compass and see how it works. If we take a magnet here and we take a needle, just a plain old sewing needle, and we stroke that needle with the end of the magnet, we'll take the north end and just stroke it, and stroke it again, and stroke it again for about a minute. That's usually long enough to align the domains in here, in this needle, so that all of their magnetic north ends are pointing this way. Then you can test that. You can place your needle on a cork or through a cork and in some water, and you can watch and see what happens. If you have successfully magnetized your needle, that end toward which you have stroked should be pointing toward Earth's geographic north. Remember, the definition of the magnetic North Pole is the one that is pointing toward Earth's geographic north. Another idea when we're making permanent magnets is to heat and then cool the magnetic material within a magnetic field. And that's why we have the picture at the beginning of this video, very cold material exhibiting magnetic properties. And heating it up allows all of the domains to move about more freely. And then cooling it down will greatly restrict their ability to move. So once we heat it up, put it in a magnetic field, and the alignment can happen much more easily because they are able to move about more freely, the domains. And then when we cool it down, those domains cannot any longer move about, and so it creates a better permanent magnet in that environment. What if I cut a magnet in half? What happens to the poles? Think about that for a minute. Okay, so if I cut this magnet right here, I really haven't done anything different. We still have a south pole and a north pole end. We have a south pole and a north pole end that hasn't changed because of the alignment of those domains. So a quick review, make sure you know what magnets are, magnetic fields, magnetic poles, know about Earth's magnetic field and magnetic materials, magnetic domains, and permanent magnets. some advanced ideas right here. Or if you have some other ideas of your own, please bring them in. Show me what you find, and I look forward to seeing you in class.